Hello everyone, in this video we are going to see how to design isolated Sqaure footing by manual approach. So first of all, try to understand the problem statement. A solid footing has to transfer a dead load of 1000 kN and an imposed load or live load of 400 kN from a Sqaure column of size 400 by 400. The material we have to use for the design of this footing is Fe415 and M20 grade of steel and concrete respectively. SBC of the soil has given as 200 kN per meter square. The allowable settlement is given as 25 mm. After understanding of this problem statement, now let's start for the design of the footing. So first of all, we need to calculate how much the total load is going to be transferred to the subsoil. So what does mean by the subsoil? First try to understand that. In any real life project, if you are going to see, so what will be there? The column will coming from the superstructure, and below to that column there will be the presence of your footing, and the soil mass that is coming under this footing or below this footing, that is called as what? Subsoil. So finally we need to calculate how much the load is coming to this subsoil. How much the load is coming to this subsoil, that we need to calculate. But in problem statement, what actually we have given? Only we have given the load coming from the column. That is what? 1000 kilonewton plus 400 kilonewton. This total is going to become what? 1400 kilonewton. But this 1400 kilonewton load is what? Is just the transfer of the load from this column. So in actual, if you are going to see, this soil mass is subjected to not only the load coming from the column, it is subjected to the load self weight of this footing also. Self weight of the footing also we need to calculate, that is going to be imposed over the soil mass, over the subsoil. So for that we need to know the dimension of the footing for finding out the self weight of your footing, self weight of your footing slab. So how you can calculate the self weight of this footing slab? So for calculation of this self weight of the footing slab, we need to know the length of the footing, we need to know the width of the footing, we need to know the depth of the footing. Unless and until you don't have these three dimensions, you will not able to calculate the self weight of the footing. Try to understand. For calculation of this self weight of this box, how you can calculate? You need to know the density of that material. This box may be of wood, this box may be of steel, this box may be of any material. But here our concern is what? It is the RCC footing, so it is the RCC element. So we need to know the density of RCC material. So we know that the density is what? 25 kilonewton per meter square for the concrete, multiplied by length of the footing, multiplied by width of the footing, multiplied by your depth of the footing. So these three dimensions we need to have. But you may ask a question, as we have not designed this footing till now, so how we can decide what is the size of footing? How we will come to know what is the length of the footing, what is the width of the footing, what is the depth of the footing? These three dimensions we don't know. So if you are not knowing these three dimensions, then how you can calculate the self weight of the footing? That's why what we are going to do, we are going to assume that the self weight of the footing is only the 10% of the total load that is coming from the column. We are going to consider the 10% of that load as the self weight of the footing. This box weight we are going to consider as what? 10% of this the load coming from your column. So total load is going to become what? 10% of this 1400 is going to become what? 140 kilonewton. That is what? Self weight of the footing we are considering. And now this is the load coming from the column. Now the load coming from the column plus the self weight of the footing combined will give you final load is going to be transferred to your soil mass as 1540 kilonewton. Here it will be what? 1540 kilonewton. Now finally, after having the load and by having the safe bearing capacity of the soil, we can calculate the in-plant dimension of your footing. For finding out the in-plant dimension of the footing, how much total area of the footing is required, how you can calculate that? So the total load, how much the load is coming, that is what? 1540 kilonewton divided by SBC of the soil. If you are going to take the ratio of the load divided by SBC, you will get the total area of the footing required. In plan area of the footing required, that you can calculate by taking the ratio of your 1540 divided by SBC of the soil. So total area of the footing required is how much? 7.7 meter square. This much area is required. So thereafter what? This is the area, but we need to calculate how much length of the footing required, and we need to calculate how much width of the footing is required. But one clue is there, that is what? Here the column size has given as what? 400 by 400. Square column is there. So experts recommends that if your column is a square column, so provide the square footing. It is better to take the square footing. But if your column is what? If your column is rectangular, 230 by 450, 230 by 600, 230 by 500. So if your column is what? Rectangular. So for that we need to take what? Rectangular footing. And if your column is what? Square column. So there is better to go with the square footing, that you need to remember. So here in problem statement, what we have given, there is a column of size 400 by 400. So there is a better to go with the square footing. There is better to go with the what? Square footing. So for square footing, it is very simple. What we need to do, we have to take what? Same length. Length of the footing we are going to consider as equal to the width of the footing, and that will equal to square root of total area required. So that is what? 7.7 total area of reinforcement required. After taking the square root of this 7.7, we are getting the length and width of the footing as required as what? 2.77. So actual length and width of the footing required as 2.77 meter. But you know that always whatever the load you are going to impose over the soil mass, the soil is giving the reaction to that application of the loading. Reaction will be there. So for the safe design of the footing, always your upward reaction, your upward soil pressure should always be less than your SBC of the soil. So to ensure that the upward soil pressure will be less than of your SBC of the soil, you should take the length and width of the footing slightly more than that of whatever there is a recommendation by the calculation. So here by the calculation we are getting what should be the length and width of the footing as 2.77. So obviously you have to take more than of this, little bit more than of this value you have to take for the calculation. So here I am going to adopt the length and width of the footing as 2.8 meter. That will be your length and width of the footing. And if you are going to find out the final area of footing where that we are going to provide here as, that will become what? 2.8 multiplied by, this is your length of footing, this is your what? Width of the footing. If you are going to take the product of this length and width, we are getting what? 7.84 meter square. So here area of footing, that is equal to what? Area of footing as provided area of footing as 7.84, which is greater than area of footing, that was the required one, that is equal to what? 7.7. So 7.7 meter square is the area of footing required, and 7.84 is the area of footing provided. So in any of the problem, while designing of the foundation, the area of footing provided should be more than of that of your area of footing required. Remember this point. Now with this calculation we are moving towards for finding the upward soil pressure. So how you can calculate the upward soil pressure? So for calculating the upward soil pressure, that will be what? Total load that is going to be transferred to your soil mass, that is how much? What? 1540 kilonewton divided by finally total area provided for the in-plant dimension of the footing. So total area provided is what? 7.84 is the area provided, and this is what? Applied load 1540. So with this ratio we are getting what? 196.43. This is what? Upward soil pressure. Safe bearing capacity is what? 200 kilonewton. Safe bearing capacity SBC of the soil is what? 200 kilonewton per meter square. and what upward soil pressure is equal to what 196.43 kilonewton per meter square. So in every of the problem or in every of the design calculation of your footing, your upward soil pressure should always be less than of your SBC of the soil. So now it is the safe one. We can proceed for the next step. After knowing the length and width of the footing, as we have calculated for these calculation, as the length of the footing we have calculated as 2.8 meter and width of the footing we have calculated as same 2.8 meter, because it is what the square footing. So length and width of the footings are same. So two dimensions we have calculated. Now the third dimension we have to calculate, that is what the depth of the footing. So what should be the safe depth of the footing? We need to calculate that. And this depth of the footing is going to be influenced by two criteria. One is your flexural criteria and another one is your shear criteria. These two criteria are there. Based on that we had to calculate what should be the safe depth of the footing. So if your depth of the footing is going to be influenced by flexural criteria, you have to check that for the shear criteria. If your depth is going to be influenced by your shear criteria, then you have to check for the flexure. So ultimately your design depth should be safe in flexure as well as in shear. So what does mean by these flexural depth requirement? What does mean by the shear depth requirement? We are trying to understand in detail. So what does mean the flexural criteria? So let's consider the sectional elevation of your footing. Suppose this is your footing slab, over that if column is coming. So here the portion which is under this column we are going to consider is infinite stiff. We are considering it as what? Infinite stiff. It means that the portion of this slab, portion of this footing slab, this I am going to call it as footing slab. So the portion of this footing slab which is under this column, this will be what? Very stiff. This is not going to be influenced by the action of this column loading. Why I am going to call it as infinite stiff? You will understand it. So under the application of this loading, and you know that there is a subsoil. So subsoil, due to action of this loading, is giving the reaction. So reaction is what coming here. So due to this reaction, and this is what the action. So action is what is going to be distributed over this width of the column. So this is what it is under the compression, and it is from the lower soil there is one upward pressure. So downward action is there, upward action is there. In between there is a slab, footing slab of this portion under this column that is going to become what? Stiff. It is not going to move anywhere. But when you talk about this portion, so there is no downward action. There is no downward action. Only the reaction from this side. There is a presence of this reaction from this side. So what possibility is there? Due to this this upward action, this projected part of the footing, it is going to be deformed like this. It is going to be what? Deformed this like this, and it is going to be deformed like this. And this response of the structure under the application of the loading and reaction, we are going to call it as flexural behavior of this footing. So here what will be there? The maximum movement, there will be the maximum movement is going to be developed over this face of this column. At the face of this column, maximum movement is going to be generated. This maximum movement. So to resist this maximum movement, how much depth is required, that we need to calculate, and that I am going to call it as flexural depth. Whatever the depth is required at the face of this column, due to the movement that is going to be generating here, to retain that movement, what depth is required, that depth I am going to call it here as what? Flexural depth. So how you can calculate this flexural depth? So before of that we need to calculate the movement. How much movement is going to be developed here in x direction, how much movement is going to be developed in y direction. So what is the concept of x and y direction? Try to understand that first. So as our footing is what? Square footing of size 2.8 meter in both of the direction. So along the length of the footing, what size is there? 2.8 meter. Along the width of the footing, I am going to call it as what? 2.8 meter. So along the x direction, I am going to consider the length of the footing. Along the width, along the y direction, I am going to consider what? Width of the footing. It is, I am going to say, width of the footing, BF. And there is a presence of column here at the center, that is what? Square column of size 400 mm. Okay, 0.4 meter, 0.4 meter. So the thing is what? We need to calculate the moment is going to be generated at the face of the column, here in x direction, along the x direction, along the length of the footing, and along the width of the footing. But one thing you can notice here, as our footing is square footing, so if I am going to calculate the moment in x direction, that will be same that I am going to calculate the moment in y direction, because everything is symmetrical, everything is what? Is square. Your size of the footing is also square, your column is also square. So this projected span will be same as that of the projected span in y direction. Okay, so how much this projected span will become? Try to understand. So total length of the footing is what? 2.8 meter. Either if I am going to consider along the length of the footing, either I am going to consider along the width of the footing. In both of the direction, what calculation will be that? It is equal to what? 2.8 meter minus, this is the total length. Okay, this is the total length 2.8 minus this part, width of the column. So column size is what? 0.4 divided by this total. I need to have, this is a total span, I need to have this half portion only, so divided by 2. So that we will get what? How much we are getting? Just calculate it. 2.8 minus 0.4, it is going to become what? 2.4 it will become, and divided by 2. So this is going to become as what? 1.2 meter. So this projected portion will become as only as what? 1.2 meter in this direction, x direction. In y direction also it is going to become what? 1.2 meter. In both of the direction, the cantilever projection, that will become what? 1.2 meter. So as earlier we have seen that under the column, the portion is what? Very stiff, that is not going to be influenced by action of the loading from the column and the reaction from the subsoil. It is not going to be influenced. Only this projected part, this cantilever portion is going to be, the stability of this projected part is going to be disturbed due to this reaction, this upward soil pressure, and due to that there is a movement is going to be generated at the face of this column. So this I am going to call it as cantilever portion. So the movement I have to calculate at this face, and this projected portion in both of the direction is how much? 1.2 meter. So upward soil pressure is how much? 196.43. So upward soil pressure 196.43, as it is the what? Cantilever. Try to understand. 196.43 multiplied by width. Very important point. Try to understand. Suppose this is the square footing and this is the column. Okay, and we are going to do the calculation for finding out the movement along the length of the footing. So this cantilever portion we have to consider. So upward soil pressure is what? 196.43 multiplied by, along the length calculation is there, so we have to consider width this much, total width, total portion. This part we have to consider. Try to understand. This complete part we have to consider actually. Okay, so width is going to become what? 2.8 meter multiplied by this projected part. Projected part is what? 1.2 meter. So 1.2 square divided by 2 for the cantilever portion, so that we are getting the moment as 396 kilonewton meter. And this is the same calculation for the y direction, because our footing is square footing, our column is square column. So that's why in x direction, in y direction, a movement will be same, 396 kilonewton meter. Okay, so this is what? Service movement. This I am going to call it as what? Service movement. Now we have to find out the factor movement. So for factor movement, just multiply this value by 1.5. So you will get the total ultimate result, ultimate movement as 594 kilonewton meter. As we are going to use Fe415, grade of steel or grade of rebar, so the formula will become mu is equal to ultimate moment will equal to 0.138 FCK BD square. This is the formula. So actually we have to find calculate how much the depth is required. So depth will equal to this formula, ultimate moment divided by 0.138 FCK into B is under square root. Okay, so depth required will equal to square root of this ultimate movement in Newton mm 10 raised to 6 divided by 0.138. FCK is how much? 20. FCK, characteristic strength of your concrete, because our grade of concrete is M20, so the characteristic strength of the concrete will become what? 20. So that will be what? 20 multiplied by whatever the width you have used for the calculation of the movement, same width you have to use here. Sometimes the students, what they are doing, they are considering 1 meter. No, whatever the width you have used for the calculation of the movement, that same width we have to consider here. If you have considered for 1 meter width for calculation of the movement, then you can use here as 1 meter. But as we have considered 2.8 meter or 2800 mm as width of the footing, okay, so that I am going to take here. And finally, if I am going to calculate, so the depth required for the footing, effective depth required for the footing is going to become what? 277.24, and this demand is for the flexural requirement. This depth demand is for what? Flexural requirement. But what I am going to do here, I am going to consider directly the overall depth as 600 mm. So you may ask a question, why you are going to take directly the overall depth as 600 as the effective depth required as 277. So slightly more than of this you have to consider as 300 or 400 something. But I am directly going to consider the depth as 600 mm. Why I am going to do this? So as I told you, the depth of the footing is going to be decided by two criteria. One is your flexural criteria, another one is your shear criteria. So this 277.24 is a demand of the flexural criteria. In most of the situation, based on my experience, the depth is going to be influenced by the shear criteria, and that will always be more than that of the demand of your flexural requirement. So here the flexural requirement is 277, but shear requirement will be more than of this, more than that of this. Okay, that's why what I am going to directly consider here as 600 mm to overall depth of the footing. Okay, now finally I would like to calculate how much the effective depth of the footing will be. So I am going to consider clear cover of the footing as 50 mm as specified. The clear cover for the footing should not be less than of the 50 mm. That's why I am going to consider here as what? 50 mm as the clear cover, and the diameter of bar we are going to assume as 16 mm. Diameter of bar we are going to assume as what? 16 mm. So it is going to become what? D available. If I'm going to consider 600 overall depth of the footing, so what effective depth will become what? Available effective depth, that will equal to overall depth minus clear cover overall. This is what? Suppose overall depth. Try to understand. Suppose this is the overall depth as 600. Then there suppose the reinforcement is going to be present here. So it is the center. So clear cover is what? 50. Then half of the diameter of bar. So 600 minus clear cover 50 minus half of the diameter of bar. Diameter of bar we have considered as 16. So that is going to become 8, and total effective depth available, it will become what? 542 mm is your available effective depth. Now the formula for calculating the percentage area of the formula for calculating the area of reinforcement required will equal to 0.5 FCK characteristic strength divided by F5 inside bracket 1 minus square root of 1 minus 4.6 into ultimate is movement divided by FCK, that is what? Characteristic strength of your concrete, but here it is already written as 20, multiplied by width that we have considered for the calculation of the movement, multiplied by depth square, effective depth square available, multiplied by width and depth. So if I am going to put all this value in this formula, so finally I am getting what? Area of reinforcement required as 3174.75 mm square. That I'm going to call it as what? Design requirement of the reinforcement. I'm going to call it as what? Design area of reinforcement required. Design area of reinforcement required in both of the direction, as it is what? It is the square footing. Okay, we have to check it with the minimum requirement of the reinforcement for the footing. So for the footing slab, as per the codal, as per the IS 456, it is recommended that minimum percentage of reinforcement should be 0.12% of B into D. So I am going to put the value here as 0.12% multiplied by 2800 multiplied by 600. So if you are going to calculate, so 0.12% means divided by 100 multiplied by 2800 multiplied by 600. Okay, so this will give you the minimum area of reinforcement required as 2016 mm square minimum area of reinforcement required, and design area of reinforcement required is what? 3174. So you know that as you can see from here, design requirement is more than that of the minimum requirement. In that situation, we have to go with the design requirement. In any case, when your design requirement is less than the minimum requirement, then we have to go with the minimum requirement. So in any of the problem, among these two value, design requirement and minimum requirement, which one you are getting the more, with that value you have to proceed. So in our proposed example here, we are getting the design requirement more. So according to this design requirement, we are going to provide the reinforcement. So as we earlier have decided that we will provide the 16 mm diameter of bar. So for 16 mm diameter of bar, unit area is how much? For 16 mm diameter of bar, unit area of bar is what? 201.06. We know that the formula pi by 4 d square. Okay, that will is equal to pi by 4 d is your 16 square. If you are going to calculate this value, so we'll get the value is equal to 201.06 something. Okay, so it is the unit area of 16 mm diameter bar. So here our objective is to find out the how much spacing is required. So spacing required will become equal to what? Spacing required over the width and length, because whatever the calculation we are doing, that is for both of the direction, not only for width, not only for the length. Why it is? Because we are dealing with the square footing. So if we are dealing with the square footing, so the calculation will be for both direction. Now here spacing required is equal to unit area divided by total design area multiplied by width considered from start. As I told you, if you have considered width as full width, so you have to consider the same width throughout the calculation. If you are going to do the calculation for 1 meter, for 1 meter width only, then you have to use everywhere as 1 meter. But in our example, we have considered the full width, so that's why I'm going to put the same full width. Okay, remember, don't do the mistake, full width. So 201.06 divided by 3174.75 multiplied by 2800 is the full width. So if I am going to calculate, so I am getting what? 177.3288. So this much spacing is required for the safe design in both of the direction. But here again I am going to directly take the 16 mm diameter of bar. One more thing, try to understand. After getting this 177.3288 mm is what? Spacing required in both of the direction. So lower value you always have to consider. So 177. So by the roundup of 25 mm, you have to consider the spacing. By the roundup of 25 mm spacing you have to consider. So if suppose you are getting 122, so you have to consider 100 lower value. If you are getting by the calculation as 171, so you have to consider 150 lower by the rounding off of 25. If you are getting 127, so you have to consider 125, like that. So here we have got the value as 177.3288.
Hello everyone, welcome you all in a new ISO certified live training program, design of substructure using CSI, Safe, Excel and manual.
In this training program, you will learn all about the concept of substructure design, commands in CSI Safe software for the substructure design, validation of CSI Safe result with your manual and advanced Excel sheets. This training program will cover 4 real-life projects. In the first and second, we will cover all the types of isolated foundation in CSI Safe software. In the third real-life project, we will cover the raft foundation. And in the fourth real-life project, there will be the coverage of pile and parapet design, design of basement wall. And at the end of this training program, you will learn how to prepare the final design sheet for the site execution. Have a look over the features of this training. Daily live classes conducted by experts. Recording of every session. Can interact with expert anytime. Exposure to real practice. ISO certification of training. It's 5-star rated training program. Till now, more than 1,000 participants have benefited from this training program. Now you are the next. So you may suggest that we should consider here as 175. That is the right one. But I'm going to take here as what? 100 mm. I'm going to take here as what? Spacing as 100 mm. Demand is what? 77. But I'm going to consider as what? 100. You may ask a question, why you are going to consider very small value of the spacing? Means more reinforcement, why you are going to consider? So you will come to know about this on later stage. Because your one-way shear check will mainly depends on the percentage of reinforcement available. That's why to avoid the failure of depth of the footing, I am trying to take in advance more percentage of reinforcement. That's why what I am going to consider 100 mm spacing, center to center spacing. If I am taking 175, that will be okay. If I am taking 150, that will be okay. But there may possibility that on later stage, when we are performing the one-way shear check or punching shear checks, so there not punching shear check, only one-way shear check is going to be depends on the presence of how much percentage of reinforcement or how much area of reinforcement available. So for one-way shear check, your percentage of reinforcement should be slightly more. That's why I am trying to what? I am trying to keep more area of reinforcement to be present. For that, I am going to reduce the spacing. So spacing I am going to consider what? 100 mm. So diameter 10 mm diameter of bar at a spacing of 100 mm center to center in both of the direction. Okay. So just come down. Now finally calculate how much area of reinforcement we have provided. So area of steel provided will equal to unit area divided by spacing that we have decided what? 100 mm spacing. Okay. Or unit area means 16 mm diameter of bar we have selected for the both of the direction. So unit area is going to become what? 201 divided by 100 multiplied by total width. So total area of reinforcement here we have provided as 5629.75 mm. It is wrong mm. It should be mm square because it is the area of reinforcement. So it should be what? It should be actually mm square. It should be what? Actually mm square. 5629.75 mm square area of reinforcement we have provided there. So percentage of reinforcement present there. So 5629.75 divided by 2800 multiplied by 600, overall depth multiplied by 100 to convert into percentage. So total percentage of reinforcement provided as 0.34 in each of the direction. In along the length of the footing, 0.34% is there. Along the width of the footing, 0.34% is there. And minimum requirement is what? 0.12%. So we have provided more than of the minimum requirement. Means our design is not safe in flexure in respect of the reinforcement, in respect of the depth of the footing. Only we have to check for the shear, for the punching shear and for the one-way shear. Now we have completed the design and we have decided that the length and width of the footing will be 2.8 meter. That is what the Sqaure footing. And we have decided that the overall depth will be 600 and the effective depth will be 542 mm. In both of the direction we have decided that we will provide 16 mm dia at a spacing of 100 mm center to center. But here one thing we have to notice that the depth we have decided here by the flexural criteria. As I told you earlier, the depth is going to be influenced by the two factors or two criteria. First is your flexural criteria, another one is your shear criteria. So we have checked and we have decided this depth based on the flexural criteria. Now we have to check this depth whether it is safe or not for the shear criteria. So when you go to check for this shear, this provided depth for the shear, so there are two shear checks you have to perform. One is your one-way shear check and second one is your two-way shear check, that we are also sometimes calling it as punching shear. Now first try to understand what is the concept of one-way shear check. So here in one-way shear check we have to find out how much the nominal shear is going to be developed at this critical section. In one-way shear check we are going to take the critical section at a distance of d from the face of the column. Okay, so at this critical section how much the nominal shear is going to be developed at this critical section, and at the same time we are going to find out how much the critical capacity at this critical section, and we have to compare this nominal shear and critical shear. So if we are shear that is going to be developed at this critical section, that we are calling it as nominal shear, if it is less than the actual capacity at this critical section, that we are going to represent by the tau c, so we are going to say safe. Our provided depth is safe, our provided percentage of reinforcement is what? Safe. But in any situation if we are getting your critical shear which is when your nominal shear is greater than your critical shear, in that situation what? Your provided depth and provided reinforcement will not be safe. You need to revise the design for the depth, you need to revise the design for the reinforcement. So in every design or in every safe design, your nominal shear should be less than the your critical shear. So actual concept is what? We need to first find out the how much shear force is going to be developed at this critical section. What my first requirement? I need to find out how much the shear force is going to be developed at this critical section. So for finding the for finding out the shear force at this critical section, the formula will become the upward soil pressure, multiply it by width available, this total width. Okay, at this critical section how much width, if I am going to do the calculation along this length, okay, so this much depth or this much width we have to consider. If you are going to do the calculation along this direction, so you have to consider this. Okay, so that much you have to consider, because our footing is the square footing. So if you are going to do the calculation along the length, that will be same as that the calculation if you are going to do for the along the width. In both of the direction calculation will be same, because our footing is what? Square footing. You need to understand this. Okay, coming back, so the formula is what? Width you have to put here, multiplied by, I need to know the this much projection, how much this projection. So how you can calculate this? The formula will become what? Total span length minus size of the column, as it is the square column, so we are making the calculation along the length. So total length minus the size of the column divided by 2. When you divide it by 2, so you will get this projection, half projection. Okay, and our intention is not to find out this total projection from the face of the column. Our intention is to find out this much projection. So how you will come to know this much projection? You need to subtract the value of effective depth. Here it is what? Effective depth. Okay, so let me first clear this all so you will understand in better way. Okay, so it is what? I need to calculate this much. Okay, so L by L minus A divided by 2 minus the effective depth, you will see this much projection. Okay, so with this formula we can calculate the shear force, and that same formula you can find in this notes. Here it is available. We are going to consider the critical section at a distance of d from the face of the column, and knowing the shear force at this critical section, and the formula is actually here it is written upward soil pressure multiplied by width of the footing multiplied by length minus A is the size of the column divided by 2 minus the effective depth. So put all of these values here, and now we are getting what? Shear force as 361.9 kilonewton. Take the factor of this by multiplying it by 1.5, so we are getting the factored shear force as 542.854, and we want to calculate the nominal shear at the proposed section, so it is going to become what? tau v is equal to vu upon b into d. Put all of these values here. So we are getting what? Nominal shear that is going to be developed at that proposed critical section at a distance of d from the face of the column as 0.358 MPa or Newton per mm square. So this is what the nominal shear. Now we have to compare this nominal shear with the critical shear. So for finding out the critical shear, we need to know the percentage of reinforcement and the grade of concrete at that section. How much percentage of reinforcement is available at that section that we have considered at a distance of d from the face of the column. So how much percentage is available here? So percentage available as 0.34%. 0.34% is available at this proposed section, and the grade of concrete is what? M20. So I need to go back to your IS 456 2000 clause number 40.4, and here you can see in table number 19 there is what? For 20 grade and for 0.2 okay, for 20 grade it is what? Different values are there. So we need to find out what percentage you want to look at the critical shear value. So go back to your calculation and see our percentage is what? 0.34. Look at this table. Is there any 0.34 exact value? So you will not able to find that because it is coming in between of 0.25 and 0.5. Okay, so in between of this value will be, so 0.25 for M20 it is 0.36 and for 0.5 it is 0.48. Just go back. So I have written the value here as 0.25 for 0.25, 0.36 for 0.5 it is 0.48. In between our percentage of reinforcement is what? 0.34. So for 0.34 you need to find the critical shear. For 0.34 percentage you need to do the linear interpolation, and with that linear interpolation you will get the critical shear as 0.43 0.403 MPa. Now compare nominal shear with the critical shear. So we are getting that nominal shear is less than the critical shear. Hence we can say that our project depth is safe for the one-way shear, as well as our project percentage of reinforcement is safe for the one-way shear. So this is the overall check we have performed for the one-way shear, and we have concluded that our design is safe for the one-way shear. Now we have to perform the punching shear check, or sometimes we are calling it as two-way shear check. So in this case we have to consider the critical section at a distance of d by 2 from the face of the column, and then we have to find out the shear force at that critical section which is at a distance of d by 2 from the face of column. So for better understanding, look at this figure. So here from the face of the column we have to consider the critical section at d by 2 along all the sides of the column. Okay, so here in this side d by 2, in this side d by 2. So total it is going to become what? This is the A dimension of your column, size of your column along this direction. Okay, so d by 2 plus A plus d by 2. So d by 2 is going to become d and plus A. So total is going to become A plus d. And if you are going to put the value, so you know that the dimension of the column is 400 mm. So I am going to consider 0.4 meter plus effective depth, you know that it is 0.542. So along this direction, this side is what? 0.4 plus 0.542. This dimension, this side and this side. Okay, both are same. So two sides these are. Third, along this direction if you are considering, so this is the d by 2 and this is also d by 2. Okay, so this d by 2 is going to become d, and this is the b. Along this direction we are going to say the dimension of the column as b, so it is going to become b plus d. So same calculation for this direction also, because your footing is square footing, your column is also a square column, so same value you will get in both of the direction. So if I want to find out the shear force at this critical section, okay, so what I need to do, the formula will become your shear force equal to upward soil pressure multiplied by the area. What area you have to put here as? Area will equal to your total area minus this internal area. Total area minus this internal area. So you will get this remaining area.
our intention is to calculate this remaining area. Okay, this outer area we have to calculate. So how you can calculate that? So very simple, you have to subtract this internal area from the total area of the footing. So finally you will get what? You will get the, if you are going to multiply that value, that area value with your upward soil pressure, you will get the shear force, and the unit will be in kilonewton. So same formula you will get here. Let me show you. Upward soil pressure multiplied by the total area of your footing minus internal area, 0.4 plus d, 0.4 plus d. Okay, so that I am going to put here as 196.43 multiplied by 2.8 is the 2.8 size of your footing. Internal size is going to become one dimension and this dimension. Okay, both sides are 0.4 plus 0.542. Okay, so same values are actually available here, and with this calculation you are getting the shear force value as 1365.706 kilonewton. To find out the factor shear force, you have to multiply this value with the 1.5. So you are getting what? Total shear force at the critical section at a distance of d by 2 from the face of the column as 2048.56 kilonewton. Okay, now the nominal shear at critical section. Here same thing you have to do as we did in the case of one-way shear. What? We need to find out the nominal shear at this critical section, and then we have to compare it with a nominal shear we have to find out at this critical section. Nominal shear, and then we have to compare it with the critical shear. Nominal shear, if it is less than the critical shear, then our design will be okay. If your nominal shear is more than the critical shear, then there is some problem. We need to change the depth. Okay, so here perimeter length of the shear. So here the formula is what? Nominal shear at critical section will become equal to what? Tau v is equal to vu upon b dash d. So you need to understand what does mean by this b dash. So b dash is nothing but the perimeter length of shear area. Try to understand. This total span you have to measure from this point to, if you are starting from this side, so perimeter, you have to add all these four sides. So here it is very simple, because all the sides are of same dimension, that is 0.4 plus 0.542. So you have to just multiply one side by 4 times. So very simple it is. Here it is what? 0.4 plus 0.542 multiplied by 4 times, because 4 edges are there. Okay, so with this we are getting the value as 3768 mm. Put all of this value in this nominal shear at critical section formula. So we are getting the nominal shear at the critical section as 1.003 Newton per mm square. This is the what value we are getting at the critical section. Now we have to compare it with the critical shear. Okay, so we need to look at IS 456-2000, page number 58, clause number 31.6.3. So come to your IS code. In IS code at the page number 58, 31.6.3.1, when shear reinforcement is not provided, the calculated shear stress at critical section shall not exceed this value, Ks into tau c. This is the formula to find out the critical shear, critical capacity at the two-way shear section. Okay, so just come here where K is equal to 0.5 plus beta c, but where the formula for the beta c is what? Shorter side of your column to the longer side of the column. Okay, so column section size, if it b by d, if we are considering column section size b by d, so width of the column, depth of the column. Okay, so but in our proposed example, the size of the column is what? Square, 400 by 400. So what? Beta ratio, this beta c will equal to 400 by 400. So you will get the value as 1. But one criteria, one limitation here it is given for the value of Ks. What criteria has given? First you need to look at this formula, 0.5 plus beta c. So if I am going to say Ks equal to 0.5 plus beta c, okay, so that will equal to 0.5, and beta c value for the considered example, it is what? Equal to 1. It is going to become 1.5, but code has limited the value of Ks to maximum of 1 only. What here it is given, you have to consider the Ks value up to the maximum of 1. So you are getting the Ks value beyond of 1, so you have to consider only 1, maximum of 1. If you are getting the lower value, then you have to consider the lower value of Ks like 0.5, 0.7, 0.8, 0.9, 0.95, so that you have to consider. But when your value of Ks exceeding beyond of 1, then you have to consider max as 1. Okay, the Ks you can find out. Then tau c, how you can calculate the tau c? Tau c will equal to 0.25 multiplied by square root of fck in the limit state method of design. And you know that we are designing our foundation by the limit state method. Okay, so that all things are actually given in your sheet. Here what actually we have given, shear at the critical section will equal to tau c into Ks, where Ks equal to 0.5 beta c, where beta c will be shorter side of your column to the longer side of the column, as we have discussed just now. Okay, therefore beta c will equal to 1. Okay, put this all value, it is going to become more than 1, but I told you maximum of this Ks value will be 1 only. You can't take the value more than of 1. That's why we are going to limit the value of Ks equal to 1 only. Who has suggested to consider this up to maximum of 1? Your IS code. IS code said that we have to consider Ks equal to 1. Put all of these values. Okay, so it is going to become what? Tau c is equal to 0.25 square root of fck. Your characteristic strength of the concrete is what? 20. So when you are going to put this value, so final tau c value you are getting what? 1.118. And here nominal shear tau v is equal to 1.003, and critical shear, critical capacity at 2A shear section, the capacity of the concrete is how much? 1.118, and nominal shear there is going to be developed due to action of the loading is how much? 1.003. So obviously the shear force that is going to be developed is less than the capacity of the section. Means on site at the foundation level the capacity is more but action is less, so we are safe. Hence project depth is safe in punching or two-way shear. So now project depth is safe for one-way shear also, project depth is safe for the two-way shear also. So now we are going to conclude that our length of the footing, our width of the footing, our depth of the footing, everything is correct, everything is safe, and our provided reinforcement is also safe. 16 mm dia at a spacing of 100 mm in both of the direction. So this is the way how to design the Sqaure footing. So it's very simple. Hope that you all understood how to design the Sqaure foundation. And after the design you have to detail it. This is the in-plan detail, where length of the footing you have to show, where the width of the footing you have to show, and reinforcement you have to show in both of the direction. Likewise sectional elevation you have to show, such that there should be presentation of reinforcement for the both of the direction. And this is what one-way shear and two-way shear check criteria.
Hello everyone, welcome you all in a new ISO certified live training program, design of substructure using CSI Safe Excel and manual. In this training program you will learn all about the concept of substructure design, commands in CSI Safe software for the substructure design, validation of CSI Safe result with your manual and advanced Excel sheets. This training program will cover 4 real life projects. In the first and second we will cover all the types of isolated foundation in CSI Safe software. In the third real life project we will cover the raft foundation, and in the fourth real life project there will be the coverage of pile and pile cap design of basement wall, and at the end of this training program you will learn how to prepare the final design sheet for the site execution. Have a look over the features of this training. Daily live classes conducted by experts, recording of every session, can interact with expert anytime, exposure to real practice, ISO certification of training. It's 5-star rated training program. Till now more than 1000 participants have benefited from this training program. Now you are the next.